Welcome to your class of Introduction to Measure Theory. We are on the third lecture, on the second part of the third lecture, in which we will prove and show the important theorem of uniqueness of measures. So the title is once again uniqueness of measures. Now we start with the theorem. The theorem tells us that if we have a space that is non-empty and you have a family inside a power set of this space that is a pi system, then it happens that the generated lambda system of f is equal to the generated sigma algebra of f. So this is a really important equality here. Alright, so the proof will proceed as follows. Since you know by definition that every sigma algebra is also a lambda system, then it is kind of, well, it is clear that since generated sigma algebras include the thing that generates the sigma algebra, so we have this inclusion, and this is a lambda system because every sigma algebra is a lambda system, then the generated lambda system of f will be inside the sigma algebra. Because this generated is the minimal by minimality. Let's write it here. By minimality of this lambda system. Now we need to recall that this is a lambda system, and f is a pi system. So from here we will show that this set is also a pi system. A pi system. Then the proposition that we proved in the previous video, in the previous part, in the first part of the lecture, will guarantee that since this is a lambda system that is also a pi system, then this is a sigma algebra, and this will imply by minimality of let's put it here, by minimality of the generated sigma algebra, that this generated is inside this generated lambda system. And this will conclude the proof because it is inclusion in both senses. So the important step will be to guarantee that this in fact happens, that the generated is also a pi system. So recall that a pi system is defined as follows. So for it to be a pi system, we need to have that x is an element of this thing, and that for every a and b inside this, then the intersection is inside it. So this is the definition of pi systems. Let me put it in a box. And we want to show this. This is to show. So the first one by the first, I mean, you need to recall that f was a pi system. So since f is included in its lambda system generated, and x, this is because f is a pi system. So this will be hold. Now we only need to prove that arbitrary intersections are held inside the lambda system. We will do this step by step, and the first step will be to define the following set. Let's fix first some f inside this family, and then define the set lambda f as every element inside is generated such that the intersection of a with f is inside the lambda system. So we need to show that this is a lambda system. Let me do it here. The definition of lambda systems is that it holds three properties, right? So the first one is that the empty set is inside this set. This is to show the empty set is inside this, and that increasing countable families, this will be inside AF. Then its countable union will be inside this thing here, and lastly that for every A and V inside this, such that A is a subset of V, then V minus A is inside this set. So we will show every step. First, it is clear that this is true because the empty set intersected with F is the empty set that is an element of this lambda system, because it is a lambda system. So this is true. For the second, let's suppose that we have an increasing family, and we want to show that this holds. So this is true if and only if the intersection of this union with F is inside the lambda system, the bigger lambda system. So by property of unions, this is the union. Let me write it here. The union of this intersected with F is equal to this thing here, and every one of these is inside the lambda system, because every AK is inside this set. So by definition of that set, we will have that this is included here. So if this family is increasing, then this new family, this new sequence of sets will also be increasing and inside this one. So this will be a set, an element of the generated by definition of lambda systems. So since this is true, then we will have this, because this means that it holds the condition by which this set is defined. So we have the second property there, And for the final property, let's suppose that we have a couple of elements inside the set such that one of them is included in the other, and let's see what happens with the difference. So difference of V and A intersected with F, what happens here? Because if this is a set, if this is an element of this lambda system, then this will mean that the difference is inside the set here. So what happens here, we can do this with a drawing. This is A and this is B, just for you to see how this works. This is A and V. The difference is this thing here, and then you intersect the difference with F, so you will have this little part here. So the question is this little part inside the intersection? Oh well, the drawing is wrong because A was a subset of B, so this is wrong. I'm sorry. So we have A here and we have B here, and F could be here like this. So A minus B is B minus A is this thing here, and the intersection with F will be just this part here. So the question is this little set inside this one? And the answer is once again yes, because you know that this is equal to B intersected with F minus A intersected with F. And these two are elements of the generated, and this one is included in the other, so this is an element of the generated. And you can see that in the graph because V intersected with F is all of this part, and A intersected with F is only this part. When you subtract that, you will have the yellow part. So it's clear that it happens because A is a subset of B. So with this, we have shown the three properties that define lambda systems. So this is in fact a lambda system. On the other hand, we have that for every, or let's say if E is an element of F, then E intersected with some F, or chosen F, is an element of F. And this is because F was a pi system. We say that at the beginning F is a pi system. So this is inside F, and F is included inside of the lambda system generated by F. So if this holds, then it is clear that E is also an element of this set, this lambda system. And then if this happens for every F, we say that F is included in this one for every F inside capital letter F. So let me highlight that here. And this is a lambda system. This is what we proved here, lambda system. All right. But it happens that our generated was the smallest lambda system that included F. So if this one includes F, then we have that this holds for every F inside here by minimality. Let me write it here. So now if we have an arbitrary f, well, we can say that for every f in f and for every a in the generated of f, this means that f intersected with a, this small f, is inside the sigma algebra. I mean the lambda system. Because every element of the lambda system is included in this set here, and this set is defined as those elements of the lambda system such that the intersection with f is inside the lambda system. So this is exactly what we wanted to show here. Now this proves this. We didn't write that well. So this is, let me write it here then, more clearly. For every f inside f and for every a inside this here, then is inside. So we highlight this part because this is important. All right, what happens now if we fixed? What happens if we fix some element of the lambda system here and we denote, so let's fix it, and we denote lambda v as every element of the lambda system is just the same as before, such that a intersected with v is inside here. So previously it was not any element of the lambda system but an element of f, which is a subset of the lambda system. Now we take it in a more general sense for every element v of the lambda system. We will prove that in fact this is also a lambda system. And how do we do this? Well, the steps are the same as before, so we will go by definition. Here, well, it is clear that the empty set is inside this because empty, we intersected with anything, is the empty, and the empty is here, so the empty holds. Then the second property, for increasing families, let's say that this is an increasing countable, increasing inside this, then we will show that the union of every k is inside this. And to do that, we just need to intersect this thing here, you know, with the fixed element v, and it's just the same as before, so it's pretty much everything the same. And so this is also true, same steps as above. And the last part, you know, for every a and let's say c inside this, such that a is a subset of c, we need to show that the difference is inside here, but that also happens due to the same reasons as the previous case. So everything is the same. This is a lambda system, you can check that on your own. And now let's go once again for the final part of the proof. Let's go once again for an arbitrary element of the family. Then this means that the intersection with v, which is an arbitrary element of the generated, is included inside this thing. This is what we proved here, because in place of a we have b, so this happens. So we have that f is inside, or else this lower letter f is inside this thing, and that happens by definition once again of the set. So this implies that f is included inside this, which is a lambda system, and then by definition, or I mean by minimality of the generated, this will mean that the generated is inside this thing here. So now take an arbitrary element of this generated, or an arbitrary couple of elements, and it will happen that the intersection of A and B will be inside this generated, because A will be inside this thing here by this part, because A is an element of this. Then by definition of this set, this happens. So yeah, this proves that, let me put it here, that the generated was a pi system, and so our starting comment will take effect. So if this is a pi system, then it is a sigma algebra, and by minimality we'll have the other inclusion, and that with the previous inclusion will imply that these two generators are equal. So whenever the collection is a pi system, then its lambda system, its lambda generated, will be also a sigma algebra generated. Now, moving on from this theorem, we have a corollary, and as a corollary, a very important result. So let's say we have a measurable space. This is the main result, in fact. So we have a measurable space and two measures, two finite measures. Let me highlight that. Finite measures. Finite measures of this measurable space. You can say that over X, and it's sigma algebra. And suppose that there exists some pi system f such that the sigma algebra is equal to the sigma algebra generated by f. So if this happens, then if for every element of this family we have that the two finite measures take the same values in this particular subset, then they are equal. As functions, they are equal. So for every element of the sigma algebra. So this is most important, because with this we only need to check whether these two functions have the same value in this small set, and then it will hold. They will have the same values for every element in the its generated sigma algebra, which can be a considerably bigger set. Because, you know, in sigma algebras you have every countable union, finite union, countable intersection, complement, set difference, and so on. So this makes you save a lot of time if you wanna do this with computations. So the proof will be the following. So let's define a subset, or well, a set let's define this set here as every element of the sigma algebra such that these two measures have the same value. This is of course a subset of the sigma algebra. So it happens that you know, f is a subset of this by our hypothesis here, that inside f they have the same value, so f is a subset of this. We will show that this thing here is a lambda system. Now it is clear that the empty set is inside this. Why? Well, because the measure of the empty set is 0 in both cases, because it is said that they are finite measures. So you need to remember that the only case in which they were not equal was when the measures were trivial, and infinitely trivial I mean that every element of the sigma algebra was associated with a plus infinity. So this is not the case, so both coincide with the value of 0. So now let's suppose we have some increasing countable family inside this set. Is increasing. We have that the measure of this increasing family is equal to the measure of the limit of ak, because you need to remember that whenever you had a family which was increasing, then its limit, well, it had a limit, and its limit was the union of every element. So we had also another theorem that tells us that this was in fact equal to this limit of a sequence of real numbers. So this was also a theorem that we proved previously. And then since every ak is inside this set, which is the set in which both measures coincide, then this is also equal to this here. And from here we have that this is once again equal to the limit of this thing, and such that this is, so this means that the union is inside this because the value of both measures on the union is the same. Now finally we have, let's say we have a couple of elements inside of the set such that one is a subset of the other. Since these two measures are finite, then the measure of a and the measure by the other function of a is finite. So we can apply that property that tells us that the measure of v minus a was equal to v minus a, which is equal to, you know, since both are in this set, to this, and this is equal once again to this. So this means that since they have the same value, that this is inside here. So with this we have shown that this is a lambda system. All right. So since this is a lambda system and we had that this is a subset of this, then we will have that the generated lambda system is a subset of this by minimality, but this is equal to this set because F is a pi system. So we have that, and it happens that, you know, the whole sigma algebra was equal to this. So we have that this is a subset, but by definition this lambda system was a subset also of the sigma algebra. So this concludes the equality, and since this set is equal to the whole lambda system, I mean sigma algebra, then the measures are equal. Now we continue with another corollary, and this will be the final corollary. So the previous was a corollary, but it was a really important result, and so is the following. So let's say we have a measurable space. Here, this is a measurable space, and we have two measures over, let's write it properly, two measures over this measurable space, and suppose that there exists a family inside this sigma algebra such that it meets three conditions. The first one is that F is a pi system, and this is equal to this, so you know what this means, all right? The second condition is that for every F here we have that the both measures coincide, and the last condition tells us that there exists some countable sequence inside of F there is increasing, such that X is equal to the countable union of all of those elements, and measure of these two things coincide and are finite. So this implies that both measures are the same. So in the previous corollary we had that both were finite measures. So if they are finite measures, then this condition happens, but it also happens that for every element the measures are finite. But now we don't have that condition. They are just measures, and it happens that inside of F, I mean of this set, they are also finite, but not even for every element of F, but for every element of this given family of increasing sets. So the finiteness of the measures is incredibly decreased. I mean, they are finite on a much smaller set than before. So not even on all the sigma algebra A, and not even on the whole family F, but on a particular subset of that set. So we will prove this. I also need you to recall that this condition means that both mu and v are sigma-finite measures. So this is a definition. So this happens whenever X can be written as a countable union of some family, and the value of the measure is finite for every element of that union. So both measures are sigma-finite. So let's say that we have, so the proof will be the following. Say that we fix some natural number and define two functions from the sigma algebra into the extended interval that are defined as, for every element of the sigma algebra intersected with this set, and the same for the other one, right? So since f of n is an element of the family, of the given family, this is less or equal than fn, and this is also less or equal than fn, because this thing is a subset of the other, and this is finite because of this. Then this means that this value is also finite. This value here is finite, and also this. So that means that these two functions are finite on the whole sigma algebra. So yeah, now let's say that we have some value here, and since f is a pi system, it is a condition of the corollary, then this can be intersected with any, in particular with this element of the family, because they are both elements of the pi system. So this is an element of the pi system by definition. And so we have that the value of this measure on f will be equal to the value of this intersected with fn, and this is because it is an element of f, which was the set in which both measures coincide. This is written here. Then this is equal to this thing here, and this is by definition this one. So this means that on f, not on the whole sigma algebra, but on f, and so the previous corollary tells us that these they will be equal on the whole. As function they will be equal because they are both finite, so we can apply the previous corollary, and yeah, so they are equal, and this holds for every natural number. So now let A be an element of the sigma algebra. We can write this as a countable union like this. This is the intersection of fn. And why is that? Well, because the union of every fn is equal to the whole space. So we can write x as x intersected with as a intersected with x, and this happens to be this thing here, and you apply the property of intersections, and you have that thing. So we have that, and given that you know, this family was increasing, then given that f is a fixed set, this is also increasing, right? So we have the following, and this will be the conclusion, that the value of this measure on A is equal, check on that, to the limit of this sequence, because this is an increasing sequence, and this is equal by the proposition that we proved in the second lecture, I think. So this is equal to intersected with Fn, which is also equal to this here, and you know that this is equal to this, and I think I'm doing every obvious step, but I'll just write everything. So this is also equal, you know, to the limit of A intersected with Fn, and this limit is of course the union of every, because this is an increasing family, so the union was A, remember, and such is the proof. So you have that holds for every A in the sigma algebra. So if this happens, then we conclude that they are both equal as functions on the sigma algebra. So it is an interesting corollary. It's in fact a corollary of the corollary of the previous corollary. Let's put a crown on this. So this is a crown corollary. So to recap, to summarize, we had that finite measures were, well, you have two finite measures that were defined on some sigma algebra, and that sigma algebra was in fact the sigma algebra generated of some pi system, and it happens that both finite measures coincide on that pi system, then those measures are the same. So this is our first corollary, and the crown corollary generalize that idea with once again we have two measures, but now they can be finite or infinite, we don't care, and we have once again a pi system inside of the sigma algebra, such that the sigma algebra is the sigma algebra generated by that pi system, and inside of that pi system the measures coincide, which could be a finite or infinite value here, could be finite, could be infinite, we don't know, we don't care. And we had that both measures, while they were not necessarily finite, they were surely sigma-finite measures. So that means that there exists some countable family, which in this case was inside of the pi system, such that well, the definition of sigma-finite measures, the whole space was the countable union of the family, the increasing family. Increasing is key, and every every value of the measure was finite. The equality is in fact a corollary of the second property. So please don't get confused. This is the fact that this sequence is increasing is not a part of the definition of sigma-finite measures. It's just a condition on this measurable space. So it's not part of the definition of sigma-finite measures. So if this happened, then both measures were the same. And with that, we conclude this lecture on the uniqueness of measures. If you have any questions, you can write it down in the comments below, and I will try my best to answer them. We will continue with the next lecture, which will be the fourth lecture, and we will talk about exterior measures and some important complicated theorem that is called the Kara-Theodori theorem, but that will be for the next day. So see you around.